Hey everybody, we're going to talk about a couple of quick ideas having to do with infinite series, and I'll do an example with these ideas in just a moment. The idea I want to get at is having to do with, so let's do it this way. Let's define a term, and then so let's see. We have. If we have an infinite series, so I could say something like, if this series made up of the absolute values of terms converges, then the series without the absolute value converges, and we say it is absolutely convergent. Okay, so that's just some terminology, right? Absolutely convergent series are really nice. A couple other features about them I want to say is, if the series, so if we have two series, the sum over a sub n and the sum over b sub n are absolutely convergent, then the sum, if we add these two series together, we get a new series which is absolutely convergent. Okay, and finally, one other thing is when, how can I say this? When a series, how about this? If the series sum over a sub n is absolutely convergent, and its sum, let's just call it S, then any rearrangement of the terms of the series also sums to S. Okay, the last one might seem silly. We're used to addition being something that we can rearrange the terms, right? It's commutative, it's associative, all that kind of stuff. But infinite series don't work so nicely all the time, right? Series that are conditionally convergent, meaning they converge, but if you take their absolute value, then they don't converge. You can actually, it is provable that you can rearrange the terms to sum to anything. Given any particular number, there is an arrangement of terms such that the sum will be that number, right? Which is a pretty strange idea, right? But this is what happens when we're dealing with infinities. Things don't work as nicely as we'd always like them to. So I'm going to do a little exercise that's going to use some of these ideas. All right, so we're going to look at a couple of things here. So first of all, let's just remind ourselves about the geometric series. The geometric series, one way I can write it down is like this, and we know that this is equal to a over 1 minus r if the absolute value of r is less than 1. Okay, so that's been shown in previous videos, so I'm taking that as a fact. So let's consider a couple of series, particular geometric series. Let's take the one where the geometric series with a equals 1 and r equals x. Okay. Well, this is the series n equals 0 to infinity. A is 1, r is x to the n. This is going to look like 1 plus x squared plus x cubed plus x to the 4th, and on and on and on, which is also equivalent to this sum still holds. A is 1, r is x. This holds as long as, oops, it should be x is less than, the absolute value of x is less than 1, okay? So this is just referring to this sum here, okay? So this sum is equal to this expression if x is less than 1. And let's take another look at, let's take another geometric series with a equals 1 and r equals negative x. Okay, so almost the same. This is going to be n equals 0 to infinity, negative x to the n. And this is going to be 1 minus x plus x squared minus x cubed plus x to the 4th, and on and on and on, right? And this is going to sum to 1 over 1 minus negative x, or 1 over 1 plus x, if the absolute value of negative x is less than 1. Okay, so just two examples of the geometric series. So a couple of things to note before we take this a little further. Both of these are absolutely convergent. Okay, right? If we take the absolute value here, if the absolute value of x is less than 1, then the absolute value of the absolute value is also less than 1. So that would still work. Same thing down here. So they're going to whenever the absolute value of x is less than 1, both of these are absolutely convergent. Okay, so these two series are absolutely convergent on this domain. This is also a good example of how we're starting to see that these series can, this is an example of a power series representing a function, right? This is the function 1 over 1 minus x represented as this power series over this specific domain, right? This is the domain of x being between -1 and 1. This is that, this is the same domain here, okay? So, so far, so good. Since these are absolutely convergent series, we can play with them a little bit. We can add them together and get an absolutely convergent series, and we can rearrange the terms and do a few things. So let's just see what this looks like. If I take the sum n equals 0 to infinity, x to the n, plus the sum n equals 0 to infinity of negative x to the n. This is going to be equal to the sum from n equals 0 to infinity of x to the n plus negative x to the n. Okay. So let's see what's going to happen here. This is the first term is just going to be the sum of these two terms, 1 and 1. So we'll get a 2. Then we get x plus negative x, so that goes away. Then we get x squared plus x squared, so plus 2x squared. The x cubes will go away. We get a positive 1 and a negative 1. The x to the 4th, we get 2 of them, plus 2x to the 4th. Sorry, I lost my train of thought for a second. Let's just write a couple more, plus 2x to the 6th, and on and on and on. In other words, this is looking like 2 plus 2x squared. Oops, sorry, I meant to say this is looking like 2 times 1 plus x squared plus x to the 4th plus x to the 6th, and so on. Okay. So what we've done is taken the sum of these two things and combined them to create a new series. All right. And one thing we might notice, let me write this out. This is the sum. This is 2 times the sum, n equals 0 to infinity, of x squared to the n. Okay, right? I just factor the 2 out front. We get a 0 when the power is 0. This is 1. When the power is 1, we have x squared. When the power is 2, we have x to the 4th, and so on. Right? Well, this is just a geometric series where x squared is the ratio. Okay. All right. Well, what do we know about the geometric series? The geometric series can be written as 1 over, this is the geometric series where a is 1 and x squared is r, 1 over 1 minus x squared. But then, of course, I've got a 2 out front, so I'm multiplying by 2. Right? So this new series we created is equal to this expression here. We're still only good if that ratio we put in, if x squared is less than 1. With a little bit of thinking, you can see that this is exactly the same as the original interval of convergence, right? Notice that this interval we ended up with is exactly the same as the intervals of the series we started with, right? And if you combine 2 absolutely convergent series this way, you'll always get an interval of convergence, or the radius of convergence, that's equal to the smallest radius between the 2 you summed. In this case, they're the same, so we end up with the same radius of convergence. Let's do one more thing with this before we go. So I want to go back to our expressions. What did we just do? We added the series for 1 minus x and the series for 1 plus x. So, sorry, 1 over 1 minus x, and we added 1 over 1 plus x. Well, if we wanted to add these 2 fractions together, we would multiply to get a common denominator. It would look like 1 plus x plus 1 minus x over our common denominator, 1 minus x times 1 plus x. In the numerator, the x's cancel. I've got a 1 and a 1. I get 2. 1 minus x times 1 plus x is 1 minus x squared, which is exactly the expression we ended up when we looked at it through the series, through the perspective of the series. Okay, so I think this is a pretty neat little little exercise that just kind of plays with some of the idea of series, and I always feel like it's a little confidence builder when there's these kind of strange ideas having to do with infinite series, but they at least, it's at least comforting to know that the same algebraic thing we get popped out when we did it using these infinite series. So there's at least some sort of consistency here. Okay, that's it for this one. I'll see you next time.